1. Introduction. This section provides a foundational understanding of key concepts in computer science and algorithm analysis. 1.1 Variables. Explanation of variables in programming languages, which store data values and can be manipulated by the program. 1.2 Data types. Introduction to different data types in programming, such as integers, floating point numbers, characters, etc., which define the type and range of values that can be stored. 1.3 Data structure. Overview of data structures, which are specialized formats for organizing and storing data efficiently, such as arrays, linked lists, trees, etc. 1.4 Abstract data types, ADTs. Explanation of abstract data types, which define a set of operations and rules for their behavior without specifying the implementation details. 1.5 What is an algorithm? Definition and explanation of algorithms, which are step-by-step procedures for solving problems or performing tasks. 1.6 Why the analysis of algorithms? Importance of analyzing algorithms to understand their efficiency and performance characteristics. 1.7 Goal of the analysis of algorithms. Objectives of algorithm analysis, including determining the time and space complexity of algorithms. 1.8 What is running time analysis? Explanation of running time analysis, which measures the time taken by an algorithm to execute as a function of the input size. 1.9 How to compare algorithms. Methods for comparing algorithms based on their efficiency, including time complexity, space complexity, and practical considerations. 1.10 What is rate of growth? Explanation of the rate of growth of algorithms, describing how the running time or space requirements increase with the size of the input. 1.11 Commonly used rates of growth. Overview of common rates of growth, such as constant time, logarithmic time, linear time, quadratic time, etc. 1.12 Types of analysis. Different types of algorithm analysis, including worst-case analysis, average-case analysis, and best-case analysis. 1.13 Asymptotic notation. Introduction to asymptotic notation, which describes the limiting behavior of functions as their input size approaches infinity. 1.14 Big O notation. Explanation of Big O notation, which provides an upper bound on the growth rate of an algorithm's running time or space requirements. 1.15 Omega notation. Introduction to omega notation, which provides a lower bound on the growth rate of an algorithm's running time or space requirements. 1.16 Theta notation. Explanation of theta notation, which provides both upper and lower bounds on the growth rate of an algorithm's running time or space requirements. 1.17 Important notes. Key points to remember about algorithm analysis and asymptotic notation. 1.18 Why is it called asymptotic analysis? Explanation of why the term asymptotic is used in the context of algorithm analysis. 1.19 Guidelines for asymptotic analysis. Guidelines and best practices for performing asymptotic analysis of algorithms. 1.20 Properties of notations. Properties and characteristics of Big O, omega, and theta notations. 1.21 Commonly used logarithms and summations. Common logarithmic functions and summations encountered in algorithm analysis. 1.22 Master theorem for divide and conquer. Explanation of the Master theorem, which provides a method for solving recurrence relations arising in the analysis of divide and conquer algorithms. 1.23 Divide and conquer Master theorem, problems and solutions. Application of the Master theorem to solve recurrence relations and analyze divide and conquer algorithms. 1.24 Master theorem for subtract and conquer recurrences. Extension of the Master theorem to solve recurrence relations for subtract and conquer algorithms. 1.25 Variant of subtraction and conquer Master theorem. Special cases and variants of the Master theorem for specific types of algorithms. 1.26 Method of guessing and confirming. Technique for solving recurrence relations by making an educated guess and then confirming the solution through mathematical induction or other methods. 1.27 Amortized analysis. Introduction to amortized analysis, a technique for analyzing the average time complexity of a sequence of operations on a data structure. 1.28 Algorithms analysis, problems and solutions. Exercises and problems related to algorithm analysis, including analyzing time and space complexity, recurrence relations, and asymptotic notation. 2. Recursion and backtracking. Exploration of recursion and backtracking techniques, which are fundamental concepts in algorithm design and problem solving. 2.1 Introduction. Overview of recursion and backtracking, highlighting their importance in solving a wide range of problems. 2.2 What is recursion? Definition and explanation of recursion, a programming technique where a function calls itself to solve a smaller instance of the same problem. 2.3 Why recursion? Advantages and applications of recursion in solving complex problems with concise and elegant solutions. 2.4 Format of a recursive function. Structure and syntax of recursive functions, including base cases and recursive calls. 2.5 Recursion and memory. Visualization. Visualization of recursion in memory, illustrating how recursive function calls are managed on the call stack. 2.6 Recursion versus iteration. Comparison between recursion and iteration, highlighting their differences in terms of implementation and performance. 2.7 Notes on recursion. Key points to consider when using recursion, including termination conditions, stack space, and efficiency. 2.8 Example algorithms of recursion. Demonstration of recursive algorithms for common problems, such as factorial calculation, Fibonacci sequence generation, and binary tree traversal. 2.9 Recursion. Problems and solutions. Exercises and problems related to recursion, requiring students to implement recursive solutions to various problems. 2.10 What is backtracking? Definition and explanation of backtracking, an algorithmic technique for systematically searching for solutions to combinatorial problems. 2.11 Example algorithms of backtracking. Illustration of backtracking algorithms for problems like the n-queens problem, Sudoku solving, and generating permutations. 2.12 Backtracking. Problems and solutions. Exercises and problems requiring students to implement backtracking algorithms and solve problems using backtracking techniques. 3. Linked lists. Introduction to linked lists, a fundamental data structure in computer science, along with various types and implementations. 3.1 What is a linked list? Definition and explanation of linked lists, a linear data structure where elements are stored in nodes that have pointers to the next node in the sequence. 3.2 Linked lists ADT. Abstract data type, ADT, definition for linked lists, specifying the operations that can be performed on them, such as insertion, deletion, and traversal. 3.3 Why linked lists? Advantages and use cases of linked lists compared to other data structures, highlighting their flexibility in dynamic memory allocation and insertion/deletion operations. 3.4 Arrays overview. Overview of arrays, another common data structure, contrasting them with linked lists in terms of memory allocation and access time. 3.5 Comparison of linked lists with arrays and dynamic arrays. Comparison of linked lists with arrays and dynamic arrays in terms of memory usage, insertion/deletion time complexity, and random access. 3.6 Singly linked lists. Explanation and implementation of singly linked lists, where each node contains a data element and a pointer to the next node in the sequence. 3.7 Doubly linked lists. Explanation and implementation of doubly linked lists, where each node contains pointers to both the next and previous nodes in the sequence, enabling bidirectional traversal. 3.8 Circular linked lists. Explanation and implementation of circular linked lists, where the last node points back to the first node, forming a circular structure. 3.9 A memory-efficient doubly linked list. Introduction to memory-efficient doubly linked lists, which use a single pointer to represent both the next and previous nodes, reducing memory overhead. 3.10 Unrolled linked lists. Explanation and implementation of unrolled linked lists, a variation of linked lists that store multiple elements in each node to improve cache locality. 3.11 Skip lists. Introduction to skip lists, a probabilistic data structure that allows for fast search, insertion, and deletion operations with logarithmic time complexity. 3.12 Linked lists, problems and solutions. exercises and problems related to linked lists, requiring students to implement various operations and solve problems using linked list data structures. 4. Stacks. An exploration of the stack data structure, including its definition, applications, and implementation details. For point 1, what is a stack? Introduction to stacks, a linear data structure that follows the last in, first out, LIFO, principle, where elements are added and removed from the top. For point 2, how stacks are used. Explanation of how stacks are used in various scenarios, such as function call management, expression evaluation, and backtracking algorithms. 4.3 Stack ADT. Definition of the stack abstract data type, ADT, outlining the operations typically supported by stacks, such as push, pop, peek, and isEmpty. 4.4 Exceptions. Discussion of exceptions that can occur when working with stacks, such as stack overflow, when pushing onto a full stack, and stack underflow, when popping from an empty stack. 4.5 Applications. Examples of real-world applications of stacks, including function call management in programming languages, undo mechanisms in text editors, and browser history navigation. 4.6 Implementation. Explanation of different implementations of stacks, including array-based implementation and linked list-based implementation, with advantages and disadvantages of each approach. 4.7 Comparison of implementations. Comparison of array-based and linked list-based implementations of stacks in terms of time and space complexity, memory usage, and performance. 4.8 Stacks, Problems and Solutions. Challenges and exercises related to stacks, requiring students to implement stack operations, solve problems using stacks, and analyze stack-based algorithms. 5. Queues. An overview of the queue data structure, covering its definition, applications, and implementation details. 5.1 What is a queue? Introduction to queues, a linear data structure that follows the first in, first out, FIFO, principle, where elements are added at the rear and removed from the front. 5.2 How are queues used? Explanation of how queues are used in various scenarios, such as task scheduling, printer spooling, and breadth-first search, BFS, algorithms. 5.3 Queue ADT. Definition of the queue abstract data type, ADT, outlining the operations typically supported by queues, such as enqueue, dequeue, peek, and isEmpty. 5.4 Exceptions. Discussion of exceptions that can occur when working with queues, such as queue overflow, when enqueuing onto a full queue, and queue underflow, when dequeuing from an empty queue. 5.5 Applications. Examples of real-world applications of queues, including job scheduling in operating systems, message passing between processes, and buffer management in networking. 5.6 Implementation. Explanation of different implementations of queues, including array-based implementation and linked list-based implementation, with advantages and disadvantages of each approach. 5.7 Queues, Problems and Solutions. Challenges and exercises related to queues, requiring students to implement queue operations, solve problems using queues, and analyze queue-based algorithms. 6. Trees. Covering the fundamentals of trees, including their types, properties, and various implementations. 6.1 What is a tree? Introduction to trees as hierarchical data structures composed of nodes connected by edges, with a root node at the top and child nodes branching out from it. 6.2 Glossary. Definition of key terms and concepts related to trees, such as nodes, edges, root, parent, child, leaf, height, depth, and subtree. 6.3 Binary trees. Explanation of binary trees, where each node has at most two children, a left child and a right child, along with their properties and applications. 6.4 Binary tree traversals. Overview of different traversal algorithms for binary trees, including in-order, pre-order, post-order, and level-order traversals, with explanations and visualizations. 6.5 Generic trees, N-ary trees. Introduction to generic trees, also known as N-ary trees, where nodes can have more than two children, along with examples and use cases. 6.6 Threaded binary tree traversals, stack or queue-less traversals. Discussion of threaded binary trees, a variation of binary trees where nodes contain additional references to simplify traversals without using stacks or queues. 6.7 Expression trees. Explanation of expression trees, which represent mathematical expressions in tree form, allowing for efficient evaluation and manipulation. 6.8 XOR trees. Introduction to XOR trees, a specialized data structure used in certain applications, where each node contains an XOR of its children's addresses. 6.9 Binary search trees, BSTs. Definition and properties of binary search trees, which maintain an ordering property that facilitates efficient search, insertion, and deletion operations. 6.10 Balanced binary search trees. Overview of balanced binary search trees, such as AVL trees and red-black trees, which ensure that the height of the tree remains logarithmic, ensuring efficient operations. 6.11 AVL, Adelson-Velsky and Landis, trees. Detailed explanation of AVL trees, a type of self-balancing binary search tree, along with their balancing criteria and rotation operations. 6.12 Other variations on trees. Brief overview of other variations and extensions of trees, such as B-trees, B-plus trees, tree, prefix, trees, and suffix trees, with their unique characteristics and use cases. 7. Priority queues and heaps. Exploring priority queues, their implementation, and the underlying data structure of heaps. 7.1 What is a priority queue? Introduction to priority queues, a type of abstract data structure where elements are stored based on their priority, allowing for efficient retrieval of the highest priority element. 7.2 Priority queue ADT. Definition of the priority queue abstract data type, ADT, including its basic operations such as insertion, deletion, and retrieval of the highest priority element. 7.3 Priority queue applications. Examples of real-world applications of priority queues, such as job scheduling, task prioritization, network routing, and event-driven simulations. 7.4 Priority queue implementations. Overview of different implementations of priority queues, including array-based implementations, linked list implementations, and heap-based implementations. 7.5 Heaps and binary heaps. Explanation of heaps, specialized tree-based data structures used to implement priority queues, with a focus on binary heaps and their properties. 7.6 Binary heaps. Detailed discussion of binary heaps, a complete binary tree where each parent node has a priority higher than or equal to its children, along with insertion, deletion, and heapify operations. 7.7 Priority queues, heaps, problems and solutions. Solving problems related to priority queues implemented using heaps, including finding the kth largest/smallest element, sorting using heap sort, and implementing priority queue operations efficiently. 8. Disjoint sets ADT. Exploring the disjoint sets abstract data type, ADT, its implementation, and various optimization techniques. 8.1 Introduction. An overview of disjoint sets, a data structure that keeps track of a collection of disjoint sets and supports operations like union and find. 8.2 Equivalence relations and equivalence classes. Defining equivalence relations and equivalence classes and how they relate to disjoint sets. 8.3 Disjoint sets ADT. Formal definition of the disjoint sets ADT, including the operations it supports such as union and find. 8.4 Applications. Real-world applications of disjoint sets, including image segmentation, Kruskal's minimum spanning tree algorithm, and network connectivity. 8.5 Trade-offs in implementing disjoint sets ADT. Discussion of the trade-offs involved in implementing disjoint sets, such as the choice between array-based and tree-based representations. 8.6 Fast union implementation, slow find. Exploration of fast union implementations with slow find operations, including the union by rank and union by size strategies. 8.7 Fast union implementations, quick find. Explanation of fast union implementations with quick find operations, including the quick union and weighted quick union strategies. 8.8 Path compression. Introduction to path compression, an optimization technique that flattens the tree structure of disjoint sets to improve find operations. 8.9 Summary. A summary of the key concepts and techniques covered in the chapter on disjoint sets. 8.10 Disjoint sets, problems and solutions. Solving problems related to disjoint sets, including implementing the disjoint sets data structure, performing union and find operations efficiently, and optimizing disjoint set algorithms. 9. Graph algorithms. Exploring various algorithms and techniques used in graph theory. 9.1 Introduction. An introduction to graph theory and its importance in computer science and real-world applications. 9.2 Glossary. Definitions of key terms and concepts related to graph theory, including vertices, edges, directed graphs, undirected graphs, and more. 9.3 Applications of graphs. Real-world applications of graphs in various domains, such as social networks, transportation networks, computer networks, and recommendation systems. 9.4 Graph representation. Different ways of representing graphs in computer memory, including adjacency matrix, adjacency list, and edge list. 9.5 Graph traversals. Exploration of graph traversal algorithms, such as depth-first search, DFS, and breadth-first search, BFS, and their applications. 9.6 Topological sort. Definition and applications of topological sorting, a linear ordering of vertices in a directed acyclic graph, DG, respecting the direction of edges. 9.7 Shortest path algorithms. Introduction to algorithms for finding the shortest path between two vertices in a graph, including Dijkstra's algorithm and Bellman-Ford algorithm. 9.8 Minimal spanning tree. Explanation of minimal spanning trees, MSTs, and algorithms for finding them, such as Kruskal's algorithm and Prim's algorithm. 9.9 Graph algorithms, problems and solutions. Solving problems related to graph algorithms, including implementing graph traversal algorithms, finding shortest paths, determining connectivity, and identifying cycles in graphs. 10. Sorting. Understanding the concept of sorting and exploring various sorting algorithms. 10.1 What is sorting? Definition and explanation of sorting, the process of arranging elements in a specific order. 10.2 Why is sorting necessary? Discussing the importance of sorting in various applications and scenarios, such as searching, data analysis, and optimization. 10.3 Classification of sorting algorithms. Categorizing sorting algorithms based on their time complexity, space complexity, stability, and adaptability. 10.4 Other classifications. Exploring alternative ways to classify sorting algorithms, such as comparison-based sorting versus non-comparison-based sorting. 10.5 Bubble sort. Explanation of the bubble sort algorithm, its implementation, and analysis of its time complexity. 10.6 Selection sort. Description of the selection sort algorithm, its implementation, and analysis of its time complexity. 10.7 Insertion sort. Overview of the insertion sort algorithm, its implementation, and analysis of its time complexity. 10.8 Shell sort. Introduction to the shell sort algorithm, its implementation, and analysis of its time complexity. 10.9 Merge sort. Explanation of the merge sort algorithm, its implementation using the divide and conquer approach, and analysis of its time complexity. 10.10 Heap sort. Description of the heap sort algorithm, its implementation using binary heaps, and analysis of its time complexity. 10.11 Quicksort. Overview of the quicksort algorithm, its implementation using the divide and conquer approach, and analysis of its time complexity. 10.12 Tree sort. Introduction to the tree sort algorithm, its implementation using binary search trees, BSTs, and analysis of its time complexity. 10.13 Comparison of sorting algorithms. Comparing different sorting algorithms based on their time complexity, space complexity, stability, and adaptability. 10.14 Linear sorting algorithms. Exploring linear time sorting algorithms such as counting sort and radix sort, along with their implementations and analysis. 10.15 Counting sort. Description of the counting sort algorithm, its implementation, and analysis of its time complexity. 10.16 Bucket sort or bin sort. Overview of the bucket sort algorithm, its implementation, and analysis of its time complexity. 10.17 Radix sort. Introduction to the radix sort algorithm, its implementation, and analysis of its time complexity. 10.18 Topological sort. Explanation of the topological sort algorithm, its applications in directed acyclic graphs, DGs, and analysis of its time complexity. 10.19 External sorting. Discussing external sorting techniques for handling large datasets that do not fit into memory entirely. 10.20 Sorting, problems and solutions. Solving problems related to sorting algorithms, including implementation challenges, optimization techniques, and real-world applications. 11. Searching. Exploring different searching techniques and their applications. 11.1 What is searching? Definition and explanation of searching, the process of finding a target value within a collection of items. 11.2 Why do we need searching? Discussing the significance of searching in various computing tasks and real-world scenarios, such as information retrieval and data analysis. 11.3 Types of searching. Categorizing searching algorithms based on their approach and time complexity. 11.4 Unordered linear search. Description of the linear search algorithm for unordered collections, its implementation, and analysis of its time complexity. 11.5 Sorted/ordered linear search. Explanation of the linear search algorithm optimized for sorted collections, its implementation, and analysis of its time complexity. 11.6 Binary search. Overview of the binary search algorithm for sorted collections, its implementation, and analysis of its time complexity. 11.7 Interpolation search. Introduction to the interpolation search algorithm, its implementation, and analysis of its time complexity, especially for uniformly distributed datasets. 11.8 Comparing basic searching algorithms. Comparing different basic searching algorithms based on their time complexity, space complexity, and adaptability to different data distributions. 11.9 Symbol tables and hashing. Exploring symbol tables and hashing as data structures used for efficient searching and retrieval of key-value pairs. 11.10 String searching algorithms. Description of various string searching algorithms, such as brute force, Rabin-Karp, Knuth-Morris-Pratt, KMP, and Boyer-Moore, along with their implementations and analysis. 11.11 Searching, problems and solutions. Solving problems related to searching algorithms, including implementation challenges, optimization techniques, and real-world applications. 12. Selection algorithms, medians. Exploring algorithms for finding the kth smallest or largest element in a collection. 12.1 What are selection algorithms? Introduction to selection algorithms, which aim to find the kth smallest or largest element in an unsorted collection. 12.2 Selection by sorting. Overview of the selection algorithm by sorting, which involves sorting the collection and then selecting the desired element based on its position. 12.3 Partition-based selection algorithm. Explanation of the partition-based selection algorithm, such as quick select, which partitions the collection around a pivot element to find the kth smallest or largest element efficiently. 12.4 Linear selection algorithm. Median of medians algorithm. Introduction to the linear selection algorithm, specifically the median of medians algorithm, which guarantees linear time complexity for finding the kth smallest or largest element. 12.5 Finding the k smallest elements in sorted order. Discussion on algorithms for finding the k smallest elements in sorted order, including techniques like min-heap and binary search. 12.6 Selection algorithms, problems and solutions. Solving problems related to selection algorithms, including implementation challenges, optimizations, and real-world applications. 13. Symbol tables. Understanding the concept and implementations of symbol tables, which are fundamental data structures for storing key-value pairs. 13.1 Introduction. An introduction to symbol tables, explaining their importance and relevance in various computing applications. 13.2 What are symbol tables? Definition and explanation of symbol tables, which are data structures that store key-value pairs and support efficient lookup, insertion, and deletion operations. 13.3 Symbol table implementations. exploring different implementations of symbol tables, including hash tables, binary search trees, balanced search trees, and other variations. 13.4 Comparison Table of Symbols for Implementations. A comparative analysis of various symbol table implementations, highlighting their advantages, disadvantages, time complexities, and suitability for different use cases. 14. Hashing. Understanding the principles and applications of hashing, a fundamental technique used in data storage and retrieval. 14.1 What is hashing? Definition and explanation of hashing, a process that maps data of arbitrary size to fixed size values, typically for efficient retrieval. 14.2 Why hashing? Exploring the advantages and use cases of hashing in various computing scenarios, including fast retrieval and efficient storage. 14.3 Hash Table ADT. Introduction to the Hash Table Abstract Data Type, ADT, which provides a high-level interface for implementing hash tables. 14.4 Understanding hashing. Detailed explanation of how hashing works, including the underlying principles and algorithms involved. 14.5 Components of hashing. Breaking down the components of hashing, including the hash function, hash table, load factor, and collision resolution techniques. 14.6 Hash table. Description and implementation details of hash tables, which are data structures used for implementing associative arrays and sets. 14.7 Hash function. Explanation of hash functions, which generate unique hash codes for input data to be stored in a hash table. 14.8 Load factor. Definition and significance of the load factor in hash tables, which indicates the ratio of occupied to total slots. 14.9 Collisions. Understanding collisions in hashing, which occur when two different keys hash to the same index in a hash table. 14.10 Collision resolution techniques. Exploring various techniques for resolving collisions in hash tables, such as separate chaining and open addressing. 14.11 Separate chaining. Detailed explanation of the separate chaining collision resolution technique, which involves storing collided elements in separate linked lists. 14.12 Open addressing. Explanation of open addressing collision resolution technique, where collided elements are placed in alternative locations within the same hash table. 14.13 Comparison of collision resolution techniques. Comparative analysis of different collision resolution techniques, highlighting their advantages and disadvantages. 14.14 How hashing gets 1 Complexity. Explanation of how hashing achieves constant time complexity for basic operations like insertion, deletion, and retrieval. 14.15 Hashing techniques. Exploration of various hashing techniques, including division hashing, multiplication hashing, and universal hashing. 14.16 Problems for which hash tables are not suitable. Identifying scenarios where hash tables may not be the best choice of data structure due to specific requirements or limitations. 14.17 Bloom filters. Introduction to Bloom filters, probabilistic data structures used for testing set membership. 14.18 Hashing, problems and solutions. Exploring common problems related to hashing and providing solutions or approaches to address them. 15. String algorithms. Exploring various algorithms and data structures for efficiently processing and manipulating strings. 15.1 Introduction. Introduction to the field of string algorithms, highlighting their importance and applications in various domains. 15.2 String matching algorithms. Overview of string matching algorithms, which aim to find occurrences of a pattern within a text or string. 15.3 Brute force method. Explanation of the brute force method for string matching, a simple yet inefficient approach to pattern matching. 15.4 Rabin-Karp string matching algorithm. Description and implementation details of the Rabin-Karp algorithm, which utilizes hashing for efficient string matching. 15.5 String matching with finite automata. Explanation of string matching using finite automata, a method based on constructing automata to recognize patterns. 15.6 KMP algorithm. Introduction to the Knuth-Morris-Pratt, KMP algorithm, an efficient string searching algorithm based on pattern preprocessing. 15.7 Boyer-Moore algorithm. Overview and implementation details of the Boyer-Moore algorithm, a highly efficient string searching algorithm based on character comparisons. 15.8 Data structures for storing strings. Discussion of various data structures suitable for storing strings efficiently, such as arrays, linked lists, and dynamic arrays. 15.9 Hash tables for strings. Exploration of hash tables as a data structure for storing and processing strings, including their advantages and use cases. 15.10 Binary search trees for strings. Introduction to binary search trees, BSTs, adapted for storing strings, with considerations for efficient searching and insertion. 15.11 Tries. Explanation of tries, prefix trees, as a specialized data structure for storing and searching strings, particularly useful for dictionary-like operations. 15.12 Ternary search trees. Overview and implementation details of ternary search trees, TSTs, which are space-efficient data structures for storing strings with fast search operations. 15.13 Comparing BSTs, tries, and TSTs. Comparative analysis of binary search trees, BSTs, tries, and ternary search trees, TSTs, in terms of their efficiency and suitability for string operations. 15.14 Suffix trees. Introduction to suffix trees, specialized data structures for efficiently processing substrings and pattern matching in strings. 15.15 String algorithms, problems and solutions. Exploration of common problems related to string algorithms, along with efficient solutions or approaches to address them. 16. Algorithms design techniques. Delving into various methodologies and approaches used in designing algorithms for solving computational problems. 16.1 Introduction. Introduction to the field of algorithm design techniques, highlighting their significance in problem-solving and computational efficiency. 16.2 Classification. Overview of different classification schemes employed in organizing algorithm design techniques based on various criteria such as problem domain, data structure usage, and algorithmic paradigm. 16.3 Classification by implementation method. Classification of algorithm design techniques based on the implementation method, including approaches like iterative, recursive, and dynamic programming. 16.4 Classification by design method. Categorization of algorithm design techniques based on the design methodology employed, such as divide and conquer, greedy algorithms, and dynamic programming. 16.5 Other classifications. Exploration of additional classification schemes used in algorithm design, including probabilistic algorithms, randomized algorithms, and approximation algorithms. 17. Greedy algorithms. Exploring the concept of greedy algorithms, their characteristics, applications, and the effectiveness of the greedy strategy in solving optimization problems. 17.1 Introduction. Introduction to greedy algorithms, outlining their nature as problem-solving techniques that make locally optimal choices at each step to achieve a globally optimal solution. 17.2 Greedy strategy. Explanation of the greedy strategy, which involves making the best possible choice at each step without considering the global impact, aiming to find an optimal solution. 17.3 Elements of greedy algorithms. Identification and explanation of key elements that constitute a greedy algorithm, including the greedy choice property and the optimal substructure property. 17.4 Does greedy always work? Discussion on the applicability of the greedy strategy, highlighting scenarios where greedy algorithms yield optimal solutions and cases where they may fail to produce the best outcome. 17.5 Advantages and disadvantages of greedy method. Evaluation of the advantages and disadvantages of using greedy algorithms, considering factors such as simplicity, efficiency, and the risk of suboptimal solutions. 17.6 Greedy applications. Illustrative examples of real-world applications where greedy algorithms are effectively utilized to solve optimization problems, such as scheduling, minimum spanning trees, and shortest path algorithms. 17.7 Understanding greedy technique. In-depth examination of the underlying principles and mechanics of the greedy technique, emphasizing the importance of making locally optimal choices to achieve overall optimality. 17.8 Greedy algorithms, problems and solutions. Presentation of problems commonly tackled using greedy algorithms along with their corresponding solutions, showcasing the application of the greedy strategy in solving various computational challenges. 18. Divide and conquer algorithms. Exploring the principles, applications, advantages, and limitations of divide and conquer algorithms, along with practical examples and solutions. 18.1 Introduction. Introduction to divide and conquer algorithms as a problem-solving paradigm that involves breaking down a problem into smaller, more manageable subproblems. 18.2 What is divide and conquer strategy? Explanation of the divide and conquer strategy, which entails recursively dividing a problem into smaller subproblems, solving them independently, and then combining their solutions to obtain the final result. 18.3 Does divide and conquer always work? Discussion on the conditions under which the divide and conquer approach is effective, highlighting scenarios where it may not be suitable for solving certain types of problems. 18.4 Divide and conquer visualization. Visual representation and illustration of how divide and conquer algorithms work through diagrams, flowcharts, or examples, aiding in understanding the process of problem decomposition and solution combination. 18.5 Understanding divide and conquer. In-depth exploration of the underlying principles and mechanisms of divide and conquer algorithms, emphasizing the importance of recursion, problem partitioning, and solution integration. 18.6 Advantages of divide and conquer. Identification and explanation of the advantages of using divide and conquer algorithms, including parallelizability, scalability, and efficiency in solving problems with inherent overlapping substructures. 18.7 Disadvantages of divide and conquer. Evaluation of the limitations and challenges associated with divide and conquer algorithms, such as increased memory usage, potential inefficiency for certain problem types, and the complexity of ensuring optimal subproblem sizes. 18.8 Master Theorem. Introduction to the Master Theorem, a mathematical tool used to analyze the time complexity of divide and conquer algorithms by providing a framework for evaluating their recurrence relations. 18.9 Divide and conquer applications. Exploration of real-world applications where divide and conquer algorithms are commonly employed, including sorting algorithms, e.g., merge sort, quicksort, searching algorithms, and algorithmic problems in computational geometry. 18.10 Divide and conquer, problems and solutions. Presentation of problem instances that lend themselves well to the divide and conquer approach, along with detailed solutions and explanations, demonstrating the practical application of divide and conquer algorithms in problem solving. 19. Dynamic programming. An in-depth exploration of dynamic programming, covering its principles, strategies, properties, and practical applications in solving algorithmic problems. 19.1 Introduction. An introduction to dynamic programming as a problem-solving technique that efficiently solves problems by breaking them down into smaller, overlapping subproblems. 19.2 What is dynamic programming strategy? Explanation of the dynamic programming strategy, which involves solving complex problems by recursively breaking them down into simpler subproblems and storing the solutions to these subproblems to avoid redundant computations. 19.3 Properties of dynamic programming strategy. Discussion on the key properties of dynamic programming, including optimal substructure. The optimal solution can be constructed from optimal solutions to subproblems, and overlapping subproblems, recurring subproblems share common solutions. 19.4 Can dynamic programming solve all problems? Analysis of the limitations and applicability of dynamic programming, highlighting scenarios where it may not be suitable due to the absence of optimal substructure or overlapping subproblems. 19.5 Dynamic programming approaches. Overview of the various approaches to dynamic programming, such as top-down, memoization, and bottom-up, tabulation, and when each approach is preferred based on problem characteristics and constraints. 19.6 Examples of dynamic programming algorithms. Illustrative examples of dynamic programming algorithms across different problem domains, including the knapsack problem, longest common subsequence, matrix chain multiplication, and shortest path problems. 19.7 Understanding dynamic programming. In-depth explanation of the underlying concepts and techniques involved in dynamic programming, including recursion, memoization, state transition, and dynamic programming tables. 19.8 Dynamic Programming, Problems and Solutions. Presentation of algorithmic problems that are commonly solved using dynamic programming, along with detailed solutions, explanations, and analyses of time and space complexities. Examples may include the Fibonacci sequence, coin change problem, and longest increasing subsequence. 20. Complexity classes. An exploration of complexity classes, providing insights into different levels of computational complexity and their implications for problem-solving and algorithm design. 20.1 Introduction. An introductory overview of complexity classes, highlighting their significance in understanding the inherent difficulty of computational problems and the efficiency of algorithms. 20.2 Polynomial/exponential time. Explanation of polynomial and exponential time complexity, discussing how the runtime of algorithms grows as a function of input size and its implications for computational feasibility. 20.3 What is a decision problem? Definition and explanation of decision problems, which involve determining whether a given input satisfies a specific property or condition, often expressed as a yes/no question. 20.4 Decision procedure. Discussion of decision procedures, which are algorithms or methods used to solve decision problems by providing an answer, yes or no, based on the input. 20.5 What is a complexity class? Definition and overview of complexity classes, which categorize sets of computational problems based on their computational complexity and the resources required to solve them. 20.6 Types of complexity classes. Explanation of different types of complexity classes, including P, polynomial time, epi, non-deterministic polynomial time, epi-complete, and NP-hard, along with their relationships and implications. 20.7 Reductions. Introduction to reductions, which establish relationships between different computational problems by transforming instances of one problem into instances of another problem in a way that preserves solutions. 20.8 Complexity classes, problems and solutions. Presentation of problems and solutions related to complexity classes, exploring examples of problems classified within different complexity classes and discussing their implications for algorithmic design and analysis. Examples may include problems like the traveling salesman problem, Boolean satisfiability problem, and vertex cover problem.